Welcome back to part two of these organic reactions. We're only going through four of them. We've gone through three already, so this is the last one. My God, oh my goodness. So this is going to be an esterification reaction. If you had to guess, what do you think we're going to make? If you had to guess, yeah, make an ester. Now, this one especially is important for you to know and understand what the functional groups are and how to name them. I always think that esters are one of the most difficult ones to name because they're always directional. They're not symmetric molecules. So we got to know what these are before we start worrying about reactions and stuff. So the esterification is a very specific reaction. We're going to make an ester. It's a subcategory of larger ones called condensation reactions or dehydration reactions in which water comes out, and in this case, water comes out. So it is a condensation or a dehydration reaction. Also, they're part of another group called an addition-elimination reaction, where you add two things together and a small molecule is squirted out. In this case, we're going to add two things together and a small molecule of water is squirted out. So let's color coordinate this stuff a little bit. I like that. So here we have an acid. I'm going to paint the acid yellow. Probably should be like pink or something. And then here I'm going to get the alcohol. So we'll need an alcohol and an acid for this to work. The acid has to be a carboxylic acid or a choo-choo. I like to do what they did right here, and that is I like to draw the two OHs pointing to each other. So the OH on this side is pointing this way, the OH on this side is pointing this way. I don't really care if the alcohol's on the right or the acid's on the right. It doesn't matter. But make the two OHs point together and then eliminate an OH and an H. In this case, they're doing this correctly in the sense that the OH comes from the acid and the H comes from the alcohol. On the other hand, if you had just picked randomly and got the H from here and the OH from here and dropped them out to form water, you would end up with the exact same molecule. It's just that this would have come from the acid as opposed to coming from the alcohol. But the final product would be the same. So in essence, we don't really care which OH we get. Just get an OH from one and an H from the other one. And we're going to just eliminate those two things. And then you're going to make the bonds stick together. Nothing else changes in the alcohol. Nothing else changes in the acid. And you just push it together to form the ester. Now, important part. This is what dictates the main chain on the ester, and that is the carbon with the double bonded oxygen. Where did you get the carbon with the double bonded oxygen? And we got it from the acid. The carbon that is single bonded only is a branch. And where do we get the carbon that's single bonded to the oxygen only? And therefore the branch is going to be from the alcohol. So the acid makes the main chain and the alcohol makes the branch. This is not so important when you build the product, but it is super important when you are given the product and you need the actual reactants. You need the acid or you need the alcohol. So let's do an actual example. This is a generic one. R groups or hydrocarbon groups. So let's move on. Here we have ethanoic acid and we have 1-propanol. It's important that it's 1-propanol because if we had 2-propanol, we'd have a different product. So stick the OHs together, eliminate the OH from the acid, and eliminate the H from the alcohol, or you could do it the other way around and get the same products, and then squeeze it together. So this is going to be a CH3, a C double bond O, and that will be stuck to something else. And this is going to be from the 1-propanol. So you get the O from it, and then you're going to get the CH2, CH2, CH3. Then again, if we grabbed the H and here and grab the OH here, then according to my color coordination, this would be from the blue one, and the product would be exactly the same. So again, it doesn't really matter which one. So if we want to name this, we would name this is the main chain, which is going to be ethanoate, and then this is going to be the branch, which is propyl. This should probably be N-propyl or 1-propyl because it's the first one. If we used 2-propanol, and therefore the alcohol was right here, then we would have a different product because it would be stuck as a branch from the second carbon. And we would call this isopropyl ethanoate as opposed to N-propyl ethanoate. Okay, let's see what you can do. Here I have ethanol and we have butanoic acid. So I'm going to write out the ethanol right here. I'm going to say it's going to be a carbon, carbon, OH, and put all my hydrogens around there like this. So IB is happy or Mr. Page is happy. And then I'm going to write down, pinning the OHs together, and I'm going to make this condensed because I'm a little bit lazy. So here we are. We are going to remove the H from here and remove the OH from here, drop that out to form water. So one of my products will be water. We have to remember a law of conservation of mass. And then we're going to draw this part of the alcohol and this part of the acid and just pin them together. So we're going to have the CH3, CH2, O, and then that's going to be hooked up to this carbon right there. It's got a double bond and everything else stays exactly the same. We don't break main chains. We're not switching things around. And that's our product. So if we had to name this, I'm pretty sure this is called water. This is going to be an ethyl group because the branch. And then this has 4 carbons, so that's going to be bute. All single bonded together, so that's an. And it's an ester, so O8. So this is ethyl butanoate. Okay, let's try something different. This is giving you a product, and now we need the reactants. So it says N-octyl ethanoate. N means on the first one, octyl means you have a branch of 8 carbons long, and ethanoate. The last one we built is the smell of pineapple, and this one is one of the components in the smell of oranges. So esters have fruity smells or floral smells, and we use those a lot with different types of fragrances, including perfumes. Okay, so N-octyl ethanoate. Okay, N-octyl is a lot. So we're going to have, I'm going to write it way down here at the bottom. So CH3, CH2, 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 1, 2, 3, 4, 5. Oof. CH2, CH2, CH2. And that is going to be bonded to the single bonded O with the carbon with the double bonded oxygen. And this is ethanoate, so single bonded carbon to one more. And that's it. That's the molecule. Now we could get all these guys and then condense them if we wanted to. We could put CH3 parentheses CH2 parentheses 7 and then have the oxygen, etc. That's another way you might see when they condense all these things up like this, is to have this kind of component. Now, working backwards, we have to figure out what kind of alcohol and what kind of acid we need to make this. So we have to recognize, and it's a little bit easier since I color coordinate it, we have to recognize that the branch comes from the alcohol. So the alcohol needs to be 1 oct N all. So we would have, again, a CH3, a CH2, and a bunch of these in a row. Can't even count. 1, 2, 3, 4, 5, 6, 7, 8. Nope, not a 3. That would be octane. A 2, and then an OH on the first carbon, because that's what makes it stick to the first carbon. And then we're going to have this part right here. It comes from the acid. Well, an acid with 2 carbons is called ethanoic acid. So that would be CH3. I can't write a 3. C double bond O single bond OH. Or sometimes they would just say CH3COOH. And these two would react together to form N-octyl ethanoate. Lots of practice you can find online. If you have any questions, ask me. I hope you enjoyed the reaction videos for organic chemistry. Yay!